Welcome, everyone, to the annual 2024 annual British Physics Olympiad award ceremony and lecture. Okay, thank you for those of you who are joining online as well as joining in person. It's a great honour and pleasure today to introduce our lecturer, Professor Mike Cates. He studied natural sciences in Cambridge and graduated with a PhD in theoretical physics in 1986. Afterwards, he moved to Edinburgh to be Professor of Natural Philosophy, which is Scottish for physics, in old money, where he was there from 1995 to 2015. Since then, he has returned to Cambridge, where he is now the 19th Lucasian Professor of Mathematics in the Department of Applied Mathematics and Theoretical Physics. And for those of you who are not aware, the Lucasian chair is one of the top chairs in the whole of the world. His predecessors include, obviously, Newton, Hawking, Dirac, Stokes, Charles Babbage, to name but a few. Because we're running short of time, this is all he's asked me to be able to say. So, Professor Mike Cates.
Thank you. Here we go. Thank you. Thanks for the welcome, and it's a pleasure to be here. So I'm going to talk today about some materials physics, or physics of fluids that stop flowing when you push them too hard. I'll explain the bulletproof custard title a bit later. But first, I'm going to introduce, I'm getting an echo. First, I'm going to introduce a broad range of substances that we, some of us in physics, like to look at. Soft matter, I'll say what they are, why we're interested in them. But I'll focus today on dense suspensions under flow, which I will explain what they are, and particularly talk about a phenomenon called shear thickening. This underlies a material known widely as oobleck in science fairs. Unlike most science fairs, I will do a demonstration, but I'll also actually explain what's going on. And that explanation is only really emerged in the last 10 years or so, maybe a little longer. So I'll say what we're trying to explain. I'll show you that with hopefully a demonstration, but also some graphs, and how we explain it. And then if I have time at the end, I'd like to say a little bit about why the knowledge of how these soft materials flow under different conditions is useful to us. First, I just want to acknowledge some of the collaborators that I've worked with over the last 15 years or so on these topics, and I won't read their names out, but there's a rogues gallery for you. And I'll just start now with the background about different types of soft matter. So here's a list of things, all of which count as soft matter: polymers, micelles, suspensions, emulsions, foams, liquid crystals. I'm not going to explain what they all are today. However, they are all around us. So polymers are what make engine oil work. They stop it freezing in winter and being too runny in summer. There are micelles. Every time you wash your hair, you're using a micellar solution of surfactants. Suspensions we will talk about today, but toothpaste is one. Mayonnaise is an emulsion. Shaving cream is a foam. Wet soap is a liquid crystal. So those are everyday examples of each of these types of soft material. And hopefully already by thinking about those things, shampoo, toothpaste, mayo, shaving cream, you sort of get the idea of what we mean by soft matter. Of course, there are kind of more high-tech examples of all of those things. All plastics are polymers. Micelles are used in pipelines to prevent turbulence. Suspensions are used to make ceramics. If you make a ceramic, you start with something which is wet, like a clay. So if you want an advanced ceramic, the kind which you have on the tiles, heat-proof tiles on a space shuttle, you have to make a synthetic version of clay with special ingredients, but it still looks like a clay, and you still bake it just the way you make pottery. Emulsions, every vaccine, or not every vaccine, but certainly RNA vaccines are held in place by an emulsion. And foams, well, you know about maybe using perhaps as fire extinguishers, but also used in cleanup. Liquid crystals, every single one of you, I expect, has liquid crystals about your person because they're in every smartphone display. So what kind of things are these at a more microscopic scale? Well, if you want to think about polymers, particularly, say, molten plastic, think molecular spaghetti. So molten plastic can flow because you have long chains, molecules in there, that can move around. They get tangled up, but they can somehow find their way out of each other's ways. So that's why that's a material which is soft. If you freeze it, which is what most plastics are at room temperature, then it's hard. But if it's molten, it's soft. Suspensions I'll talk more about. If you want to think about that, think about microscopic ping pong balls floating around in water, for example. And the liquid crystals which are in your smartphones are molecular needles. So I could give a lecture on each of these topics, but I'll just stick with the middle one today. But the broader theme is, if you know what's in one of these materials, how does the internal composition and the structure of what's in there control its macroscopic behavior, with a particular focus on how it flows, because that's the characteristic property of soft materials. They can easily change shape, and much more easily change shape than volume in general. So that's what I want to focus on. Right, so let me talk about dense suspensions. So here's some movies. Hopefully you can see these. The left one, these both look like computer simulations, but the left one's actually an experiment. That's a suspension of little particles which are a few microns in size. You can think of them as little spheres of polystyrene in water or another solvent, and that is being subjected to a flow. The thing on the right is a computer simulation, and what we saw there was a shearing, this is in 2 dimensions, of disks. And one of the things you can see there is that the flow is very erratic. So over a long time scale, you might see, or macroscopically, you might see smooth flowing material there, but if you look at what's happening, so those red lines are telling you where the contacts are between particles, and I'll come back to the role of particle contacts a bit later on. That. Okay, so I want to talk about liquids. So the simplest liquids are called Newtonian liquids, not because they obey Newton's first, second, and third law, but because they obey an equation which I'll show in a minute, which is Newton's law of viscosity. So it's in his Principia, of which there's a copy in the library here, although I don't think you'll have time to see it before you go home. So imagine a block of material with a fixed plate at the bottom and a moving plate at the top. I move the plate with a horizontal velocity v, and I'm going to call that gamma times the height of that block. So gamma is a dimensionless measure of the rate of shape change, or the rate of strain it's called. As a result of that, to cause that, I have to apply a certain force at the top, and it has to be a force per unit area. And the ratio, the force per unit area is called the stress, shear stress. So shear stress, Greek letter sigma, is force per unit area. Strain rate, I'm going to give this Greek letter gamma, is the speed of the top plate divided by the thickness of the sample. So that's the rate at which the thing is flowing, essentially. So Newton's law of viscosity is extremely simple. It says that the stress I need to apply to change the shape of the material at a certain rate is proportional to that rate. And the constant of proportional, Greek letter eta, is the viscosity. So you can view that as a definition of viscosity, but there is a empirical law there which he discovered experimentally, namely that for simple liquids, such as water, the stress is proportional to the strain rate. For the liquids I'm going to talk about today, that isn't so. But if it is so, I have basically a linear plot here of stress versus strain rate. So graphs of stress against strain rate are going to be central to my talk, and I'll do a lot of graphical explanation of things. So straight line, slope, eta, and different slope for different temperatures, or whether you're talking about water or olive oil or whatever. This is what Newtonian fluids do. However, the fluids that, or the soft materials that I'm talking about today tend not to be like that. So in the jargon, they're non-linear. What you have is something called a flow curve. So the stress is a function of the strain rate, but it's not a straight line. And it can bend either way. So these are called non-Newtonian fluids. And examples of Newtonian fluids on the left, water, olive oil, honey, that's the non-solid version of honey. Molten glass, well, solid glass maybe. But things like spit, engine oil, putty, molten plastic, dense suspensions, the kind of things that I mentioned at the beginning, so containing polymers or suspended particles, are non-Newtonian. They have these funny shaped flow curves. So it looks like I'm going very quickly through my summary here, but there will be a long pause at the explanation stage. So I'm going to talk about shear thickening suspensions. So as I say, many of you have seen these things. You can make them in your own kitchen. I will do a demonstration, I think, probably now. So I'm now going to move to the front, and let's see if we can get the video camera up here. So, many of you, as I say, will have seen this. Okay, so here, let's see which way. This way. Let me point at this camera. Yep, there we are. Okay. So this is corn-starch suspension in water, and you can make it yourself. It's also, you can make it yellow if you buy custard powder instead of cornstarch. That's the only difference between custard powder and cornstarch is the yellow dye in custard powder. Right, so the point about this is it clearly is a liquid. So I can stir it like this. I can swill it around. But as you also perhaps have seen, strange things can happen. So among the stranger things that can happen is this. So this has unusual properties. Essentially, it is a liquid which appears to be Newtonian if you put a very small stress on it. But if you put a bigger stress, it stops being Newtonian. And in fact, it turns into something which most people would describe as a solid. So let me show you a bit more of this. I should be looking at that camera, shouldn't I? Okay, I'm now going to pour this in here. So, bit lumpy, you might say. It's worse than that. It basically stops altogether if you put too much stress on. Well, not quite altogether. There is, however, at least a factor of 1,000 difference in viscosity between this thing, if you want to call it a liquid, and it's what we're seeing in the tank at the bottom under conditions where you stir it very slowly. So in other words, the sigma of gamma curve here, the stress as a function of flow rate, is so nonlinear that it really requires explanation. Now I'm going to just leave that there. And you can watch it gradually. So it's important to realize that it's not that the water is coming out first and the particles are left behind. This stuff that's coming out now is exactly the same as what came out at the very beginning. Okay. So I advise the experiment if you've not done it at home. Oh yeah, here's the YouTube video of somebody running across a swimming pool full of that stuff. I'll just quickly show it. Yeah, he's sunk in, but that guy runs across the top. Okay. So, yes, and if you read the Daily Mail, you can read about bulletproof custard. So, in fact, there are armored vests which basically have this inside them. The idea being, when the bullet arrives, it goes solid. Until then, you can move around. Thanks to someone called Norman Wagner, or Wagner, as he in fact is called, at the University of Delaware. So that's the bulletproof custard story. Now, this is beginning to flow in the wrong place, so I'm just going to quickly take this away now. Oop. No need for camera. I'll just leave it like that. Okay. So here's a plot of the stress against the rate of strain for a material very like that. It's not just cornstarch and water, there's lots and lots of these. So what you can see is something which is, this is a log plot, by the way, since the funny scales there. So what you see is at low stresses, it behaves in a roughly Newtonian fashion. Then suddenly there's a fairly narrow range of stress, shear rate, if you like, at which the stress leaps upward by 2 orders of magnitude in this case. And the other thing, the red arrows there, it actually says that it's called hysteresis. It means if you go up, you jump at the right-hand curve up to the higher viscosity or the high stress branch. If you come back down, you may come down at a slightly different point, or a very different point in some cases. So slightly more complete set of experiments. This data here from a group in Edinburgh, which I used to be in. This was taken in 2016. Phi here is an important parameter in these systems. It's basically, if you have spherical particles, which cornstarch is not, but that's a detail I will ignore today. Phi is the concentration measured in a dimensionless way, n being the number of particles times their volume divided by the volume of the liquid that they occupy. So that's a dimensionless measure of concentration. And you can see at low concentration on the right, the black curve there, actually the behavior, it is non-Newtonian, but it's basically smooth. If you keep increasing the concentration, you see these increasingly vertical flow curves. So something is definitely happening around the point where the green data kicks in. So the red and black curves are referred to as continuous shear thickening, and the green, blue, and purple ones are called discontinuous shear thickening, and that's what you're seeing in the cornstarch. So if you look in detail at what's going on there, what you can also find is that if you apply either a constant, so you would say you're doing this experiment with the flow with the force across the top, either apply a constant stress, or you might just move at a constant rate, and in either case you'd measure the other of those two things. What you find is that they tend to be time dependent. In other words, you move with a constant stress, the force is wobbling around all over the place, the flow rate rather, and vice versa. So you get these chaotic, different types of flow behavior, which I don't want to go into the details, just to say the unsteadiness of the flow is a feature which, again, I think you could see in that demo. So here's one example. Here's a system which is, you're forcing the top plate to move at a fixed speed, and you're measuring the stress, in other words, the force you need to do that, and you see these oscillations here. So there are instabilities of the flow connected with this type of behavior. And this is a chaotic one. Right. So the long explanation. So it's taken a long time to explain this, partly because as physicists, particularly theoretical physics, we like to simplify. And we tend to simplify things as much as we can, and then maybe sometimes forget the simplifications that we've made, which might not quite be up to the job. And that's really the story of the preceding 50 years of research on this topic, which we had to kind of slightly rethink when we were looking at this before. However, the data, those flow curves, and this performance that you saw can be explained with a specific scenario. I'll now tell you the scenario and then spend most of the rest of the talk explaining it. So the scenario is this. Imagine that I have, for instance, cornstarch at low volume fraction, so low particle concentration, relatively dilute solution. It is going to be Newtonian. So say I just put 10% of cornstarch in water. If I increase the volume fraction, that's continuous shear thickening. So is that. But if on continuing to increase the volume fraction, I had a stress as a function of the rate of strain, which hypothetically looked like that curve, and then maybe ultimately this one, then in fact all of the observations that I've described briefly can be explained. For example, it's possible to show mathematically that wherever you have a negative slope on this curve, the flow will be unstable. So the observation of these oscillations and chaotic behavior and so on is consistent with that. And the other thing is that if I look at the S-shaped curve in the middle there, okay, so that, by the way, the way in which the flow is unstable, say at that green point, is just like a particle sitting at the top of this double weld potential here. If I change the stress a little bit downwards, the system is going to flow faster, which is totally contrary to what you'd normally expect. So that instability is just like having a particle at the top of a potential like that. You push it epsilon off to the side, and it will go to one branch or the other, either the upper or the lower branch of the purple curve here. But also this effect of hysteresis, if you're increasing the stress, or the strain rate rather, so imagine I'm increasing the strain rate coming along the bottom curve here, I can't go past that right-hand kink. I mean, the system has to jump to the top curve. So that's the discontinuous shear thickening. The system has to, as a function of the rate of strain, there has to be a discontinuity in the steady stress, if the system is steady. And coming down, again, you can come back down in a different place. So that's basically the explanation of what was going on in that graph I showed you earlier. So sudden stress jumps and hysteresis are associated with having a putative flow curve, stress as a function of strain rate, which is S-shaped. So that's what we're searching for. We're searching for physics which can give us S-shaped flow curves in dense suspensions like the cornstarch. So why is that a difficulty? That, I think, yes. Here's the problem. So suppose I'm focused on this case here. I want to get a flow curve that looks like that. So physics, that curve has a place where the wiggle is. I can either think of that as some characteristic rate of strain or some characteristic stress at which the system is going to have these changes of behavior. So we need some physics which sets the scale for a stress or a rate of strain, which I'm going to call sigma star or gamma star. So that, you think, shouldn't be too difficult. Let's do a little bit of dimensional analysis, so-called. The dimensions of stress are mass, length to the -1, time to the -2. The dimensions of the strain rate, as I said, that was it's telling you the motion of the top plate divided by the height, so that bit's dimensionless. It's a velocity, so it's 1 over time. So those are I need to find something in the physics that has those dimensions. And the problem is, for many decades, physicists looking at dense suspensions have been using what I'm going to call the standard model of dense suspensions, which is basically microscopic ping-pong balls in a Newtonian fluid, such as water. And I'll just show you, we can't find a stress or a characteristic time from the physics that was traditionally used to explain these systems. So suppose I have little hard spheres in a Newtonian solvent, such as water. The viscosity of the solvent I'm going to call eta S. That has mass, length -1, t -1. That's the dimensions of viscosity. And the other important thing is to realize that inertia is negligible for the kind of system I've been showing you. So if I think of a particle, radius r, the type of system we're thinking about here, r may be few microns. I can imagine applying a force to it. And it's in a solvent, so the solvent will resist. I have to create a flow in the solvent. So there's a force from the solvent. And the sum of those two forces is the mass times acceleration. There's a formula for the solvent force, which is proportional to the velocity. If a particle moves through a Newtonian fluid with velocity v, the force that it feels from the solvent is proportional to the solvent viscosity, its radius, and then a factor of 6 pi that you don't need to worry about. Right, so the interesting thing is that if I take, say, the particles in cornstarch or in any of these other of these shear thickening suspensions, imagine that I have such a particle and I don't apply any force to it, but it's moving at the moment. It feels this acceleration, which is proportional to viscosity. And what you find is a particle which is moving but not being pushed in a Newtonian solvent, if it's a few microns in size, comes to rest in a microsecond. So that's not the scale of time on which you saw the phenomena in that pot there. In particular, the characteristic rate of strain at which the wiggle needs to be is something like 1 reciprocal second, not 10 to the 6th. So what that means in practice is that in the range of flow regimes that we're interested in these suspensions, the applied force and the solvent force have to balance, and the acceleration is negligible. So that means that the mass of the particle doesn't enter. That's the standard picture. And it will still be the standard picture when I've finished. Okay, so negligible inertia, so there's no other mass. And then the other simplification which has normally been used to talk about these systems is to think about the interaction force between particles as something very simple. Basically, it's called the hard sphere interaction. You just say, I've got particles, and they're macroscopic, they're solid, they cannot sit on top of each other, but as long as they're separate, that's fine. So if I think of that as a force as a function of the separation x for two spherical particles, what that says is the force, this is now not the force caused by the fluid, but just the direct force between the particles. It's 0 until they touch, and then it's infinite. Basically, can't overlap. So the radius of the particles comes into that force law, so I have a length, but there's no time from there. And the interaction force, because it just goes straight from 0 to infinity, again, no length or time. So if we take what I'm calling the standard model, I have this problem. I can't make something with the dimensions of stress or strain rate from the physics that I think I have, which is the particle radius, the interaction force, and the solvent viscosity. So you feel like you can think of that as a no-wiggle theorem. So we have to find a way around the no-wiggle theorem, and that means finding some new or different physics that I have left out of this picture so far. So just to summarize that, what it means then is that because there's no wiggles, if I take microscopic ping-pong balls in a solvent, they can increase the viscosity. The macroscopic viscosity of that suspension can be vastly bigger than that of the water, say, which would be true even in the slow flow regime there. Or if I put in too many particles, it might stop flowing altogether. Those are the things that I can have, either a perfectly Newtonian liquid or a solid. And if I think of phi as this dimensionless, the volume fraction, the measure of particle concentration, the viscosity of this Newtonian fluid would be a function of that. And if I add too many particles, that viscosity could actually become infinite. So every curve on the left is linear, but the slope might reach infinity for some particular concentration, which is called the jamming point. So it means if I put in too many particles, the system will stop flowing altogether. Its viscosity will be infinite. So there's a key parameter of this picture, which is the jamming point. And that's going to be an important player in the kind of revised picture that I shall now tell you about. Right. So a surprise, which I suppose is now about 10 years old, is the answer to the question, what controls this jamming point? In other words, what does the jamming point depend on? And the answer is, it depends on something I haven't included so far, which is friction. So if I think of two particles pushed together like that, so under conditions where the flow is trying to push the particles together, they have a normal force Fn, equal and opposite, Newton's appropriate law, and a tangential force which can be large or small, according to the law of friction. So it's just the same as having a block on a sloping plane. You have gravity, the tangential force that the friction of the plane between the plane and block can apply is limited to some constant times the normal force. So that's the friction coefficient. And even though these particles are suspended in a fluid such as water, if they come into actual solid contact, solid to solid contact, they can have a friction. And indeed they do. And that friction coefficient can be measured in various ways. And it was found that it has a strong effect on phi j in a careful and cunning sequence of experiments that I won't describe here. For our purposes, the importance for this, for the getting wiggles on the flow curves, is that if I have a small friction, say 0, then that contact can slide sideways. If I have a large enough friction, it can't slide. I'm pushing the particles together, and then they have to roll. So the friction has an important effect on the local dynamics of the particles. They can slide, or they may have to roll, depending on the strength of the friction at the particle contacts. Why does that matter for phi j? Well, it does. And that, let's just see, oh yes, here. To understand that, we have to make a kind of slight conceptual leap. So on the left is one of these suspensions, drawn in 2 dimensions for simplicity. And the red bars there are just in my imagination. They're just joining the centers of particles which happen to be in contact. But there's a connection between that picture and the one of the bridge there, which is a classical problem which was actually studied by James Clerk Maxwell in the 19th century. And he asked the question, suppose I have a structure, like a bridge. How many connections, how many bolts do I have to put in to stop that thing from falling over? What is the connectivity I need to make it rigid? So for instance, if I take 4 struts like that and I join them at the corners in that way, but I allow the angles to change, that's floppy. Square is floppy, triangle rigid. So if you have fixed joints, you constrain the angles and the lengths, and if you have hinged joints, you constrain the lengths only. So there's a deep echo between that, very classical calculation and what's happening in our suspensions, because I have to decide what is going to happen when the particles can slide and what can happen if they can only roll. So that connection was made by this man, Sam Edwards, who actually was my PhD supervisor many years ago. So he asked about the contact network of particles in a suspension, or indeed in a material such as sand. It's the same question. How many contacts do you need for rigidity? And the rolling contacts constrain the angles of these red lines here, as well as the separations between the particles, sliding contacts, separations only. So it's extremely similar to this Maxwell calculation. And here's the answer. So this is in D dimensions. So 3 being the number of dimensions we usually have, but this with D equals 2, I get the picture at the top left there. If there are a fraction f of contacts which are rolling with 2 constraints each, and the others, 1 minus f, are sliding, then the number I need per particle varies between 6 and 4. So, and this number of contacts per particle is traditionally called z. So z of phi is some function, which I'll talk about in a minute, but if you ask the question, is this particle packing rigid? It depends on the fraction of slidable contacts through that formula there. And if they're all slidable, you need 6 particles around you to stop you being rigid, and if they are all only can roll, it's 4 in 3 dimensions. Right. So that's why friction matters so much, because it means that this jamming point, which is the density at which you have enough contacts to be rigid, depends on whether you have rolling frictional or sliding non-frictional contacts. The jamming density for spheres, and their numbers for corn-starch are higher, but that's because they're not spherical, but that's an empirical thing one could check, 58%, 64%. And those are the volume fractions in a packing of spheres at which the coordination number z is respectively 4 and, 6 and 4. Right. So the idea then is that I can take my, the picture I had before and add this idea of friction, but it's not actually changed anything, because the only thing I've added is mu. That's dimensionless. So I can't introduce a wiggle with just mu. I have a more rich picture now, though. I still have these straight lines, so I can have any Newtonian viscosity I want, and what's more, the viscosity as a function of the volume fraction could blow up in different places according to whether I have a lot of friction at the contacts or very little. Right. So remember, this is what we wanted, and we're now well on our way. So the physics which is missing, as we now realize, is that the particles in a typical hard sphere suspension, or indeed any shear thickening suspension, in cornstarch, for instance. In cornstarch, they're not spherical particles, but the generalization of what I've said carries through to the funny shaped particles. They're not quite hard sphere either. They can't overlap, but as they approach, actually they're slightly charged. And so they feel a bit of extra repulsion. And that's quite general. And normally, if you say, well, you know, this force is about to diverge. It's about the important thing is they can't overlap. But actually, there's an important thing here, which is that there's a certain scale of force, which is now F star, which is where they can overcome these, say, charge interactions and come into contact, bang. So that's what we need, it turns out. So having an additional short-range repulsion with some characteristic scale to it, F star, gives a stress scale. I can turn that into the units of stress by saying F star divided by the particle radius. So basically, if I have a contact knowing that there's a few contacts per particle, and I want to figure out what's going to be the force on the top plate, that's the way I do the calculation. So the idea now is that there is a characteristic stress. And for low stresses, the contacts are mostly frictionless and particles can slide, and for high stresses, they're mostly frictional and particles have to roll. So that means that this jamming point is now a movable feast, depending on the stress. And this is the key piece of physics which was missing until 2014. So notice I can have as a function of the stress, I can say, well, with an interaction like this, there'll always be some particles some pairs of particles which are, the force is weak enough to be still sliding. But the dependence of the fraction of rolling or contacts F of sigma, which is going to go from low to high at around sigma star, that is going to be totally smooth. This is an average over trillions of different contacts in different parts of the system. So there's going to be some smooth population level function for the fraction of rolling contacts as a function of the stress that I'm applying. But joined onto this idea of the jamming, that turns into a wiggle, as we'll now see. Right. So on the left are two flow curves for Newtonian system, two Newtonian systems. The green one is a system without friction, and the blue one is a system with friction. And as I've said, the jamming point depends, it moves from 64 down to 58%, say, for hard spheres. So what I've done there is I've got that slightly to the left of the lower jamming point. And now I'm going to draw across two horizontal lines and say, if the stress is much higher than the purple one, I'm going to be on the upper curve because I'm talking about the frictional case. And if it's below the yellow horizontal line, I'm going to be on the lower green curve. So that smooth F there translates into this smooth red flow curve. So the stress as a function of the rate of strain now has this non-Newtonian character to it. And a smooth F translates into a smooth flow curve. But now I'm going to imagine taking phi, that's the concentration of particles, progressively to the right, towards phi r. So perhaps you can see what's happening. The blue curve has gone up a lot in slope. The green, not so much. More of the same. Because I'm approaching this divergence in the viscosity for the frictional particles, this has to develop a wiggle. Because I've said I'm on the blue curve at high stresses, I'm on the green curve at low stresses, I must have a wiggle. And on we go. And if I actually reach the phi r, I have this. So, that's just what we needed. What that says is, because of the way that the friction in the system depends on the stress, I can, out of a series of what are individually Newtonian curves, I build up these composite curves which say high friction at high stress, low friction at low stress, and I get exactly the sequence of curves that I told you earlier on explain the behavior. So that's good. So this is some results from the computer simulation, just because in the computer simulation you can specifically decide what interactions you're putting in. You can measure the individual particle contacts, and you can also measure the macroscopic behavior here. What's plotted here is the viscosity against the strain rate for different volume fractions in 3 dimensions of hard spheres, with a rule saying that if the force between 2 particles exceeds some threshold, F star, that's a frictional contact. So a very simple rule. So you get the non-Newtonian behavior, you get the continuous shear thickening, and then on the red one you actually get a discontinuity, which basically means there's some non-monotonic S-shaped curve underneath this, which the system avoids by jumping. In the same computer simulation, you can measure the fraction of frictional contacts as a function of the stress, and it's completely smooth. So it's important then to have that distinction. I'm not wiring in some discontinuity into the microscopic physics. The microscopic physics is a smoothly behaved function of the parameters, and I could use any reasonable f function here, and I'd still get a jump because of the way the curves have to fold over as I increase the slope of what was the blue line relative to the green. Okay, so in case you thought that was too easy, you could equally have a theory where which flow curve you're on, if you like, whether you have friction or not friction, depended, for instance, on the flow rate. I said it depended on the stress. In a Newtonian system, that's the same, because the stress is linear in the flow rate. So if you depend on one, you must depend on the other. But if I tried exactly the same game by saying, oh, the friction between particles is activated only at high velocity rather than high force, then I would be drawing 2 vertical lines on that plot. And I'd say, okay, on the left of the orange vertical line, I'm in the low friction branch with the low viscosity on green. And on the right of the vertical purple line, I'm on the high friction branch, which is blue. And I do get a non-Newtonian curve, but that curve will never fold over. It has no reason ever to turn backwards. The left curve must turn backwards if the slope of the blue line is sufficiently larger than the green. Okay, so let me say just a little bit about why this might matter. I hope it matters to you, because I think it's absolutely gorgeous piece of physics, although I'm boasting rather to say that. But one also might, try to explain to someone who you want to get some funding from, if you're an academic. So what's the backstory in terms of the applications? Right. Well, if I've understood this scenario, suppose I have a problem like that in my chocolate factory, which I will explain in a second. What it means is if I can go in there somehow and change the friction between particles, in particular, if I can add something, a slippery molecule, which dramatically reduces the friction between particles that are in contact, then I can push phi r towards phi s. Because the friction coefficient mu, which I kind of tacitly assumed was very large in drawing this picture, is basically abolished. So these 2 curves, you move right over there. So there's 2 advantages of that. Firstly, that means I can still flow at a higher concentration, and for reasons I'll explain in a minute, that matters in a lot of industrial processes. Also, I'm Newtonian, so I don't have this kind of problem. So, chocolate. So I never thought when I entered the world of physics that I would write a paper with chocolate in the title, but here it is. There's a process called conching, which is how you make chocolate, and it involves you make chocolate molten. And you have cocoa solids, you've got cocoa butter, which molten is a liquid, and you put the cocoa solids back into the cocoa butter with sugar and with milk, powdered milk, in fact, if it's milk chocolate. Here's a very small chocolate factory, but nonetheless, the key thing is you make about a ton of chocolate at a time. And this process of conching, which is basically mixing those ingredients to make a nice, smooth, flowing molten chocolate, takes hours or days in a hot, high-energy mixer. And actually, if you're worried about the carbon footprint of your chocolate bar, which you should be, that is it. That's what dominates that. This is what it looks like. So this is some molten chocolate. Now, if you look at the surface of that, you can see it's developing these creases and crinkles, which is actually the same as I was showing before. And the reason is this is engineered to have just as much solid as you can pack into it, and it still be flowing. So that's why, if you look on your chocolate bar, you will always see soy lecithin. There's also something called PGPR, which is in most chocolate bars. So these are often listed on the ingredients as emulsifiers, but this is what they actually do. So here's my molten chocolate, cocoa butter, melted cocoa solids, some sugar, skimmed milk. So basically, this molecule, this is lecithin, coats these particles. Of course, they're not spheres, but humor me. And it makes them much more slidey. So this has been, part of chocolate making for decades, if not centuries, and I think ours was the first paper to actually explain why this works. And it does, as I've said, this is the viscosity as a function of the lecithin content. But yeah, there are things that the conching process has to achieve, which requires some, difficulty in the flow. But ultimately, this is why there's the control of frictional contacts, which is why these small amounts of these slippery molecules are crucial in making chocolate. Now, once you realize that this is true in lots of other areas as well. Setting cement, is one. If I also mentioned this thing before of the artificial clay and making ceramics, again, it's got as much solid in the suspending fluid as possible. Same thing applies. You can get that under much better control with friction modifiers, and you need dense mixtures of particles in a liquid matrix to make battery electrodes, etc. So understanding the jamming mechanism is the key step, because then you can control it, and understanding the key step is friction, which tells you how to control it. Right. So just to finish, the game isn't over. Given that I'm a professor of mathematics, you saw very few equations. After Newton's, viscosity equation, there was, well, a bit around the friction. But I managed to explain most of that with graphs. But if you want a predictive theory, you've got to have equations. And in particular, if you want to have a theory which explains what happens when I deliberately impose a time-dependent stress or a time-dependent flow, and I'm interested in what is the other one doing. So for instance, I could do an oscillatory flow, or I can be shearing this way and oscillate it that way, which turns out to be a good way of unjamming things, by the way. You need a theory. So we're still working on that theory. We have kind of various versions of it. What's plotted here is an experiment where you have a steadily shearing system close to this shear thickening transition. So it's, well, in fact, it's past the shear thickening transition. So it is very, very slow to shear, and then suddenly you go into reverse. And then if you think about it, I've got this packing, these particles are all kind of pushing against each other, go into reverse, all these contacts open up. The ones which were pushing become pulling. And indeed, the viscosity collapses. And then after a while, it rebuilds for the flow in the reverse direction. So there is experiment on the left and numerical experiment, on the left, and kind of equations theory on the right for this process of reversal. So we're still working on how to understand more general flows. So that was my talk, mostly dense suspensions, shear thickening. I hope I explained and showed you the phenomena and how we explain that in terms of relatively simple physical contexts. And thank you for your listening.
Hello. Thank you very much, Professor Cates, for an absolutely lovely talk. I hope those of you in the audience who are currently in school can see that it isn't all about reductionist physics. I think a lot of you, when you're in school, that was definitely my case. I was interested in reducing to the fundamental laws, but just because you have those fundamental laws doesn't mean you can build up your knowledge of the world from those microscopics. And today we had a really lovely talk which showed you that even though a lot of the physics is very well known in some sense, there's still quite a lot of richness. And indeed, it's more than just single particle physics, which is what you typically do in school. Let me just quickly explain what we need to do in terms of the questions. So can we switch over to the Slido slide, please? So those of you who are online and those of you here in person, we would like you to send in questions via this QR code, slido.com, with that number. So I'll give you a few moments to type some of those in. Thank you for those who have given me questions so far. I will pass them to Professor Cates directly. You've got a lapel mic. So I'll read the question in order for it to be on the stream. So I'll pick which one, probably this one first, because it's a nice non-technical one. Okay. So question number one, as we get started. What inspired you to study this? What inspired you to study this topic and to give this lecture?
So topic first, that stuff with the cornstarch, I first thought about when I was at school. And I didn't imagine that my research career was going to take me to solving that problem in any sense. But when I saw the possibility of doing that, I thought, I'm not going to let someone else be first to that one. So in between, of course, I studied lots of other soft matter problems, polymers particularly, and I mentioned micelles. So, and the reason I was interested in those, because there's this, as Anton mentioned, if you've got a particle, you can talk about, planetary orbits, you can do all kinds of things. If you've got billions of particles or Avogadro's numbers of particles, the behavior that comes out of Avogadro's number, or actually much less than that for these, but billions certainly, of interacting particles is not something you can guess by just looking at the force between two particles. It's a collective emergent phenomenon. And that's what my career, that's what has interested me from the beginning, is how often quite terrestrial and even kitchen phenomena emerge from the interaction of very, very large numbers of relatively simple interacting particles. In terms of choosing to give this talk and not another talk, I do have one other talk only. I'm a theorist, so this is an experimental demo that I can do. I have one other talk about viscoelastic micellar solutions, which, as I mentioned, shampoo. Actually, quick while we're on it, COVID, hand gels. Why does the hand gel come out of the bottle? If you look at the stuff in your hand gel, it's got a little nozzle. The hand gel is a viscoelastic solution. If you measure its viscosity at low force, at low stress, there's no way it would come out of that bottle. You could hold it upside down and squeeze as hard as you like, and you just get kind of the odd drip every 30 minutes because it's extremely viscous at low stress. You squeeze it, poof, out it comes. And that has a flow curve which is also S-shaped but lying on its side. So that's another example which I could have used.
Okay. So if one wants to do the cornstarch practical at home, how does one do it?
You go to your supermarket and you buy cornstarch. And you mix it with water, but what you do is you start with it dry, you add a bit of water, and you keep adding water until the system behaves as I've shown it. It's as simple as that. If you add too much, of course, you better have some spare cornstarch to thicken it up again. But it's what you have to realize is when you don't believe you've done it, because when you've made it, you still feel this isn't properly mixed, because you're stirring it and it goes dreadfully lumpy, and you think, well, no, the water is separated from these solid bits and I need to mix them up. No, you need to be patient and just let it relax. If you leave it overnight, you do have to resuspend it because eventually the particles sink and you get a layer of clean water on the top.
Okay. Does the hysteresis curve imply that the system has memory of a previous state? And if so, what is it remembering?
That's interesting. That's a very interesting question. I'm slightly confused because I'm not sure that the hysteresis curve itself implies memory, but I can say there definitely is memory. It does remember. And this was partly what I was explaining with this flow reversal. If you have a system that you're shearing in this direction and you stop, inside the network will remain anisotropic, ready to support or to oppose that shear, which is why when you reverse it, it does something totally different. So as someone actually mentioned in one of the Olympiad talks, Brownian particles. I didn't mention Brownian motion. For small particles, Brownian motion is important. These particles are a bit bigger. You don't have to worry about the fact that just thermal energy is causing them to move around. What that means is if you, at any point, if you stop the flow, every particle stops moving in 10 to the minus 6 seconds. And so that, whatever state it's in is remembered until you move it again. And that will typically be a highly anisotropic state corresponding to the direction in which you were last shearing it.
What are the direct applications of this theory? Can it help people get unstuck in quicksand?
Quicksand, that's slightly different. Yes, I think I probably shouldn't try to explain quite why quicksand is not the same as this. Quicksand is a little bit opposite because actually it liquefies when you try to escape from it, so you get sucked in. So yes. So I wouldn't say quicksand, but well, I think I mentioned with chocolate and some of these other industrial systems where you need to control a flow which would be otherwise extremely erratic. I should say that if you get jamming like that in a factory with a suspension moving along a pipe, you can destroy. So I showed you that little kind of mini chocolate factory. Those mixers, they cost hundreds of thousands of pounds. You can break them, literally, if you get this wrong.
Okay. Something about how you go about doing physics. So this was an example of what I call real physics. What's the relative fraction of computational experiments, real experiments, and doing analytical work?
Well, in practice, these tend to be done by different people. So the new experiments I showed near the beginning were done by my experimental colleagues, as I was then in Edinburgh, particularly the team of Wilson Poon. So at that time, I was working very closely with them on a lot of different topics. So I would say, at the moment, in this kind of area, I think roughly equal effort on those three has been very productive for us. But in other slightly different fields, you'd want a lot more effort in the experiment because the theory might be simpler or vice versa, potentially.
Okay. How well do these findings appear to apply to non-spherical particles? So you've mentioned using a spherical approximation.
Yes. So I use the spherical approximation to get actual numbers, like phi for frictional particles, the jamming concentration is 58%, and for sliding ones, it's 64. Actually, for the cornstarch, these numbers are more like high 70s. So, but if you think of what I said about if you have if I have a packing of non-spherical particles, I can still ask what is the constraint at a contact? How many degrees of freedom does it actually constrain? And this is like this kind of Maxwell calculation. And the sliding versus rolling still applies for non-spherical particles as long as they're smooth. So there will be a generalization of this argument for any smooth particles, regardless of their shape. What I can't do is predict the exact numbers, but the scenario of having two jamming transitions and a evolution from one Newtonian curve to another one as a function of the stress is intact.
Okay. Going back to your earlier point about stopping bullets, is it actually likely to be able to work?
That's a very good question. I think actually they seem to work better with daggers than bullets. So I've seen demonstrations where you try to stab these vests, and it's quite... What they actually have is they have a shear thickening suspension like this, but actually it's laminated with Kevlar. So Kevlar, as you may know, is an extremely tough fabric. And it's the combination, I think, of those two things. So the Kevlar is keeping the colloidal suspension highly confined, because if you... I hit this with a mallet, and you saw what happened, but if you stab it, it can kind of leap up in the air. You can fracture it. But if you keep it confined between layers of Kevlar, then it does the shear thickening job for you. So I don't know if they are actually in use as bulletproof clothing, but Norm Wagner, this guy, has the patents. So I'll ask him next time I see him whether he's making money from this.
Could they be used, for example, on speed bumps? So if you go at particular speeds, you hit a brick wall, and if you don't, it's better.
That's a really cool idea, actually. Patent that one. Excellent idea.
Okay. So how can material properties such as Young's modulus be determined for non-Newtonian fluids that behave both like a solid and as a liquid?
Yeah. Well, so I mean, when you saw me pouring that cornstarch, I mean, I could do a Young's modulus experiment on it. It would have to be done fairly quickly, but you can certainly try to stretch it, and you could see, you know, what is the force per unit extension. But then, of course, if you do that and then hold, you know, the force will disintegrate. So, I mean, the theory of this type of system is part of this whole, a big established theory of which, you know, Newtonian fluids with a viscosity and Hookean solids with a Young's modulus are two, you know, corners of this big space. And in between, you need a rather more complicated language than just viscosity and elastic modulus.
Okay, I have to ask an AI one because what's the role of potentially using AI to help you develop theories?
Very interesting question. I've not thought about it in precisely this setting. There are other problems that we've worked on and others have worked on, and whilst I've not used it myself, I've seen other people do really very interesting things. So there's a part of what we do when you get past the graph stage and onto equations. We have a lot of the mathematical description of these flowing systems tends to involve partial differential equations. So if you've heard of the Navier-Stokes equation, that is one. So with partial differential equations, particularly in systems like this where you're not maybe quite sure what the physics is, what is actually possible to do is say, I'm going to assume that there's a partial differential equation, and I'm going to give my AI a library of terms that it might include. So I can think of the terms which might be allowed in principle by symmetry or other considerations, and then ask the AI, given a bunch of experimental data, which are the terms that actually matter for those kinds of systems. We've not tried it here. I have seen it work specifically for liquid crystals.
Okay. And then final question for today. Are there limits to where this model would work and stop working?
Oh, well, I'm sure there are. Yeah, so something of course there will be lots of systems where this isn't the physics, but I think most of the systems that behave like the one I showed you, it is. But something else that can happen, which you can see a bit in the experiments, one of the things which distinguishes the flowing branch from this jammed one is that the surface of the material is shiny and smooth at low stresses when it's very gently being stirred. If you hit it hard or stir it fast, it looks like it's dried out. So there's something called dilation, which is the tendency of particles when they jam to try to kind of expand to get out of each other's way. So there are aspects of this which I've not talked about, but if you think about a blob of that stuff, then you need a theory which knows about the fact that the blob has an edge. All the theories I talked about, I was just like a continuum material which might as well be infinite in all directions, just a stress as a function of strain rate. But if I have a blob, it turns out that I can, in some of these systems, I can get a droplet, droplet material, say 5 millimeters across, which can be a liquid droplet, or the same droplet can be the jammed solid droplet, and what's more, once it's jammed, it stays jammed until I do something to turn it back to the liquid. And that's because the surface tension around this droplet is enough force to hold the particles in their locked frictional state. So I think there are a number of directions in which the theory could go, but I don't have time to say much more.
Yeah. Well, I wish to thank Professor Cates again, but before I say that, I was actually quite worried about him bringing in various demos, but he assured me that he has right of access to the Royal Society because amongst his many awards and prizes, he's a fellow of the Royal Society, so he can bring things in without being stopped or arrested. With that, can we give Professor Cates a round of applause?